All right, we are recording. I forgot to turn on projector and turn that on. But I have a fairly major announcement to make. I think I gave you the good news, bad news situation before, right? I've got another good news, bad news situation. And this is inexcusable. This is this long. But I was just told that sometime back in June, around maybe June 12th or something like that, Governor Kay Ivey announced that July 5th would be counted as a state holiday as well as July 4th, because it's a Friday and we'd have a long weekend. Okay? Our administration did absolutely nothing with this. I didn't even know it happened. But she made the announcement, like I said, at least 2 weeks ago, more than 2 weeks ago. And so I had heard Thursday when I was over on the Birmingham campus from a secretary, "Did you hear we're getting off early on Wednesday?" I said, "No, I hadn't heard that." And no one had heard it. She said, "Well, yeah, because the governor said we have, Friday was a holiday. Of course, we don't work Fridays, so that made state employees have a 24-hour week. A 40-hour week would be 5 days. 3 days would be 24-hour week. 3 times 4, 20. 3 times 8, 24. Well, we worked 4-day work week, and we worked 10-hour days in June and July. So 10 and 10 is 20. Plus 4 on Wednesday would be 24. But nothing had come out about it. Not by this morning when I started class. So after my first class was over with, I went down to check to see if anyone had seen or heard if they had made an announcement. No, they hadn't. So I started calling around. Either got no answer or people just didn't know. So finally I called the vice president's office, and she said, "Well, they're still trying to decide on that." I said, "Well, what do I tell my classes? I have a class meeting right now." This was after 11:30. I said, "I need to tell them whether they're going to have class Wednesday or not." "Oh, well, I'll give you a call." I said, "Well, I'm going to be in class." "Well, I'll send you an email." "Well, I have someone tell you." Well, they came out with this 12:45 today, okay? A good hour and 15 minutes into my last class, and someone brought it up to me and said, "Due to the fact that Governor Ivey is recognizing July 5th as part of the July 4th holiday, the college will close on Wednesday, July 3rd at 12 o'clock noon. This means we have 24 o'clock hours work for staff. We'll be working 10 hours today, 10 hours on Tuesday, and Wednesday we'll work for 4 hours. All classes beginning after 12 o'clock on Wednesday, and all Saturday classes." There aren't any Saturday classes this summer, so I don't know where that came from. "Will be canceled. We'll resume the regular classes on Monday, July 8th at the normal times." Now, are any of you also taking A&M classes on this campus? Because they do have some. Not this campus, Lawson campuses. They will be notified and will determine when those classes operate. Have a happy 4th. So, bottom line for us is sad news. We don't have class on Wednesday either. Sorry about that. So we just have class today and none on Wednesday. And I forgot to mark the roll, and I misplaced my pen. Oh, there it is. Okay. Okay. Let me also mark. All right. Corbin's not here. Ricky is here. Happy July, by the way. Tavin's not here. Matthew's not here. Rachel's not here. Carlton's not here. Nolan's not here. David's not here, but Jasmine is. One at the top and one at the bottom. So glad y'all are here. Okay, let's go from current slide. And this is where we left off before, I think. Yeah. Now, last time we talked about directional derivatives. Do y'all recall what they were? Earth to class, okay? If f is a differentiable function of x and y, then the directional derivative of f in the direction of the unit vector u, which is cosine theta I, sine theta j, is du. Now u is, by the way, unit vector, okay? The directional derivative in the direction of u of f of xy, which covers the whole surface, so the directional derivative in any direction, not necessarily the x or y direction, any direction, would be the partial of f with respect to x times the cosine of the angle plus the partial of f with respect to x times the sine of the angle. Now, sort of a problem with this, they say it's a directional derivative, but notice it's not a vector. It is a scalar quantity. It's the slope, basically, of the curve in the direction of this unit vector, but it's not a vector itself. It's just the slope of the curve in that direction, the directional derivative, okay? I hope I'm saying that correctly. They don't ever quite say it that way. And of course, if this was, the unit vector was the I only, then this would be partial of f with respect to x times cosine of 0, which would be 1. So that would just be the partial of f. That's your derivative in that direction. If it was in only the j direction, then that would be your angle then would be 90 degrees, or pi halves, and that would be partial, and sine of pi halves is 1. So your directional derivative would be exactly what you would expect, the partial derivatives. Okay. All right. Now, let's do, follows that there are infinitely many directional derivatives of a surface at any point, one for every direction specified by any unit vector you happen to choose. They just show a few here. This is not quite in the direction of the x in the I direction. This is something a little bit, very small j, negative j. This would be almost a diagonal, not quite, maybe a little more x and y. This would be more y than x. This would be negative on x, but slightly positive on y. This would be negative on x and y. This would be positive on x, but negative on y. And you could draw as many arrows as you wanted to in there, infinite number of them, to show which direction that would be. You have to, whatever direction it happens to be going in, that would be your directional derivative. Okay. And two of those are the partials of f. I just said this, I didn't know the slide was coming. When your unit vector is the I vector, then you have just partial of f with respect to x. When the unit vector is the j vector, okay, then the unit vector, then your directional derivative would be just your f sub y, because this would be 0. Okay? Make sense? All right, I think we're ready for example 1. Here it is. Boy, it seems like they do have to work for you here. No, not necessarily. Find the directional derivative of this function, and this is a differentiable function, continuous function, polynomial function, perfectly good. This is a surface, function of x and y. at the point 1, 2, in the direction of, okay, so they give you the point where this is, okay, x equal 1, y is equal to 2, and here's your unit vector in the direction pi thirds in the I direction, well, pi thirds, okay, if this is x and this is y, pi thirds would be 60 degrees, something about like this. So cosine pi thirds would be the I component, sine pi thirds the y component, x component, y component. Okay, so how do you do this? Let me get my pen set up. All right. Directional derivative in the direction of this unit vector u, okay, of the function f of x and y would be what? I'm sorry? Yeah. Okay, let's go back and see. Here it is. It's the partial of f with respect to x times the cosine of theta plus the partial of f with respect to y times the sine of theta. Okay, so obviously a couple things we have to do is f sub x. And what's that?
2x.
Negative 2x. Okay, and f sub y is negative 1/2. Second? Y, right? Okay, negative 1/2 y. Okay, so this would be minus 2x cosine pi thirds minus 1/2 y times the sine of pi thirds. Well, we know what x and y are. Here's our x, there's our y. So negative 2. And what's cosine of pi thirds? Anyone remember? No, that's the sine of pi thirds. Yes, 1/2. Okay. Minus 1/2 of 2 is 1. And what's the sine of pi thirds? Root 3 over 2. So this would be minus 1 minus root 3 over 2. So that would be minus 2 minus root 3 over 2. Or minus 2 plus root 3 over 2. However you want to write it. Okay. Whoops, 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 whoop, 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 whoop. Oh, yeah, okay, no. Like I first said it, minus 1 minus root 3 over 2, which when they do their calculation of that, they get negative 1.866. Okay. Now, you can interpret that as the slope of the surface at the point. Now, they said at the point 1, 2, 2. What do we mean by that? Well, when x is 1, that would be 2 minus 1 squared is 1 minus 1/4 of 2 squared, which would be 2 squared is 4. Well, I don't know where I got a 2 from. That's a 4. Okay. 4 minus 1 minus 1, which is equal to 2. I think I was already subtracting in my head. Okay, so therefore the point is x equal 1, y is equal to 2, z, which is alpha of x, y, is also 2. So that's the point there. So this would be the slope in that direction. Okay? Now, by the way, this figure that we have here, z is equal to 4, I can't write, minus x squared minus 1/4 y squared, okay, which you could rewrite as x squared plus y squared, 1 plus 1/4 y squared plus z is equal to 4, or x over 2 squared plus y over 4 squared plus, that's y, x squared and y squared, z over 4 is equal to 1. That is an elliptic paraboloid, okay? And of course, you're coming downhill when you're at 2, 1, because the maximum is up here, whatever that happens to be. At perhaps 4, yeah, or 2, or somewhere up there, and you're coming downhill, so it's not at all surprising that your slope is a negative slope. You're coming downhill at the point 2, 1, 1, 2. Okay, let's see if they show it. I think they will. Oh no, yeah. Let me clear my scratch out of the way. Okay. And because alpha sub x1 is equal to minus 2x, alpha sub y, xy is negative y over 2. They're both continuous. This is differentiable. You can apply theorem 13.9, so the directional derivative would be alpha sub x cosine theta, alpha sub y plus alpha y sine theta, which is minus 2x cosine theta plus a minus 2y, y over 2 sine theta, which would be theta equal pi thirds, x equal 1, y is equal to 2, produces directional derivative in the direction of alpha. In the direction of u of alpha at 1, 2 would be minus 2 times 1/2 plus minus 1 times root 3 over 2, which would be minus 1 minus root 3 over 2, which is about negative 1.66. Now this is better than me drawing this. This is as I said, an elliptic paraboloid. The paraboloid is down like this. Maximum value is 4. You're going downhill from 4 till you get to the point 1 on x, 2 on y, and then go up to your surface here. And you see, certainly in the direction of pi thirds, that would be from the x-axis, 60 degrees or pi thirds degrees here, so they drew it about right, and in that direction at that point. This is in the xy plane down here, is that vector here, so this is going downhill here, going downhill pretty quickly, and that's the slope of almost 2, negative, downhill, okay? Now, they're skipping example 2, so let's back up and do example 2. Any questions on example 1? Okay. Example 2. And this one you can go to larsoncalculus.com for an interactive version of this type of example. Find the directional derivative of alpha of xy, and this is x squared sine 2y. Certainly x squared is a continuous function. Sine of 2y is a continuous function, so we're happy there. At the point 1 root 2, 1 pi halves, Okay, so x equal 1, y is equal to pi halves. Okay, in the direction of, goodness, I got to sneeze, sorry. Sorry about that. Whew. In direction of, here's your directional derivative v is 3i minus 4j. Okay, we're calculating directional derivative. We want the directional derivative in the direction of that vector there. V is equal to 3i minus 4j. Okay. Now, what are a few things you need to do? You let me know.
You have to do the same formula, the directional derivative.
Okay, you're going to do the directional derivative at that point in that direction. Okay? And what steps do you need to do? What actual?
Find the partial derivative.
Okay, partial of f with respect to x. And what is it in respect to x?
2x
Of 2y, perfect. Okay. How about partial of f, the partial of f with respect to y?
cosine 2y.
Okay. And yeah, 2. Okay, you'll have a 2 there. And I also like to put my x squared in front too. Okay, so I'm going to put 2x squared cosine 2y. Because if I put it, the 2 or the x squared or anything else after the cosine of 2y, almost looks like that's part of the argument. It's not. It's out front. Okay? Okay. What else do I need to do? Anything?
Then we can plug it into
I'm sorry?
plug it in into the direction.
Okay, and what is that? I want to call that capital D. Okay. Is it V?
No, it's D.
In the direction of V? Oh, in the direction of U. What's U?
U is 1.
What's that?
Say what's U?
Yeah.
U is equal to the cosine of pi over 2.
Okay. So, all right. Tell me what to write, and I'll try to write it. Okay, du. You said U.
Yes.
Okay. And what is U, did you say?
U is the cosine, right?
Okay. Are you saying U is that unit vector?
Yeah.
Okay.
So we have the V.
Say again?
We have the V.
Oh, we have V. So what do we put here?
So
V or U? Huh?
it would be V. V for this one.
Okay. Now, I hope I'm not being too obnoxious, but use of V,
Then
F of X, Y. We could put in the values we will in a minute. And what would that be?
then it would be the partial, so 2x sine 2y.
Okay. So you got your 2x times the sine of 2y.
Plus
All right.
2x squared cosine 2y times the sine of pi over 2.
Oh, pi over 2. Okay. Okay. Not quite. What you were saying originally was right. You need the unit vector here. That's not a unit vector. So you either have to find the unit vector that's in that direction. Or you take this and divide by the magnitude of that. You can either divide first and then do it later, okay, because you need that to be a unit vector. This is a notation, but it's not the same as that. That would be the same if this was a unit vector, cosine, sine. What we have here is okay, the unit vector in the direction of V would be, remember how to get a unit vector? Second? Okay. That's not quite the same thing here. The unit vector in this direction would be V divided by magnitude of V. Remember? This is unit vector in the direction of V would be, you have to be in the same direction of V, but divide by its magnitude so you make it a unit vector whose magnitude is 1. And what is the magnitude of V? So this would be 3I minus 4J. What's the magnitude of V? Square root of what? 9 plus 16, which would be 25. Square root of 25 is? So that would be 3/5 I minus 4/5 J. There is the thing. Now, you don't plug this in. This is the point. This isn't the unit vector. So that was the other thing you got a little crossed up here. You don't need this now because you know what the magnitude, what those components are. You dot, you multiply f of this by the I component. Before it was cosine theta. Now that component is 3/5. That times 3/5, this times 4/5. Okay? And then figuring what this is, plugging in x equal 1 and y. See, this is the y value. That's not your theta. That's your y value. This is x, there's y. So this will be 2 times 1, which is 2, times the sine of 2 times pi halves. What's 2 times pi halves? You don't need a calculator. 2 times pi halves is pi. And what's sine of pi? 0. Sine of pi halves is 1. 0. So this one completely goes to 0, plus 2 times 1 squared would be 2, times the cosine of pi. And what's the cosine of pi? Negative 1. You're right. Negative 1 times 4/5. Okay? So this would be minus 8/5. That would be its directional derivative in the direction of that vector v at this point, xy. So you see, you don't plug in the cosine of these. That's the y value. You plug that in to get the first part, not the second part. And the cosine theta and sine theta, that's exactly what your components are of that unit vector. Okay, cosine theta would be 3/5 and sine theta would be 4/5. So that's what you plug in there. So negative 8/5. Now I don't know what this is exactly. They show it in the book, but this shows you're going downhill a little bit better than a slope of 1. The figure in the book, to me, isn't a great figure. Here's Davis. I got more bad news for you, Davis. Were you here last time when I told you, of course, the good news, bad news situation? Mm-hmm. Oh, it was. Last time I said the good news was the bad news. Bad news was 4th of July was Thursday. We weren't meeting, but the good news was, the 4th of July college is closed. The good news was on Wednesday, we are meeting because that has changed. Governor Ivey proclaimed that Friday would be also part of the 4th of July holiday, but since we weren't coming to school on Friday, that meant that state workers only had a 24-hour work week, and we were working 10-hour days, so 10 hours on Monday, 10 hours on Tuesday, that's 20 hours, 4 hours on Wednesday, no class. That's the abstain. Sorry about that. Get over it, okay? You promise you will? Okay, good. So we've just been doing example 1 on top of page 921. Chapter 13 is functions of several variables, and 13.6 is directional derivatives and gradients. Oh, and by the way, let me also say this. I probably should have said this at the beginning of the class with so few people here, but let me say it now so I'm thinking of it. I finally got most, not all of your stuff on Blackboard. I got your syllabus out there. I got my locator card out there. I've got the research paper instructions out there. And I have PowerPoints through, I can't remember what chapter. I think I'm into chapter 15.1 or something like that. So everything we've done so far, plus some, is there. I've still got a few more to do in chapter 15, but after that, well, and then I've got some other websites to link up. Other than that, your Blackboard is just about completely set up now. I don't have anything in the grade book yet. I'll get to that when I can, but I do have that set up. So just to let you know that's happening. And then we will not have class on Wednesday. Okay. Now,
Section 13.5, right?
What's that?
Section 13.5.
This is 13.6 that we're in now. Yeah. Directional derivatives and gradients. 13.5 was chain rules for functions of several variables. Okay. And we're just in the second example here. Now, I think one thing I messed up is I did it up here but didn't do it down here. That's a minus 4/5. So this is a minus 4/5 here, and that makes it a plus 8/5. Yeah. Just happened to notice that this is a minus here, so the unit vector would be a minus in the right part, and then you have the minus of cosine and the minus of that makes it a plus 8/5. And that makes it going uphill a little ways, just a little bit better than 2. You're going in the direction of positive 3 in the I direction, negative 4 in the J direction. That's your unit vector. Positive 3 in the I direction, negative 4 in the J direction. And I do not see how this blue line in your text is anywhere close to your directional derivative. Okay? That's nuts. I could kind of see it on the other one, but I cannot see it on this one at all. I think they have the wrong line in here. I'm not drawing it. I'm not about to draw it. But you see, if I'm understanding right, that's the directional derivative up here, and that looks to be in the direction of u here. Well, here's the direction of u here. How in the world can this line that looks like it's perpendicular to it be in that direction? It can't be. This would need to be going up the hill like this. I'm about to lose the book. Up like this, you know, a slope like this, not quite two. So that blue line, I don't know what that blue line represents, but it's surely not the directional derivative, the tangent line there. That's perpendicular to you, not parallel to you. So unless I'm missing what they mean the blue line to be, they just have it wrong. Okay. 8/5 was the answer, going up the curve there. Now, any questions on directional derivatives? Okay. Now we're going to talk about another concept, and this is a gradient of a function of two variables. Now remember I said the directional derivative is the derivative or the slope of the tangent line in the direction of some vector, v. You need to make it a unit vector to do your calculations, but in the direction of some vector v on the curve, in that direction. It's a slope, but it's a scalar quantity. It's just a slope, you know, positive, negative, up, down, you know, gradual, slight, whatever. Okay. Now what the gradient of a function is in two variables, in some ways it's sort of related, but in some ways it's very, very different. The gradient of a function in two variables is a vector-valued function, not a scalar, like directional derivative was, but a vector-valued function. Here's the definition of it. Definition of a gradient of a function of two independent variables. Let z equals some function of x and y. Okay, there's your function. Be a function of x and y such that f sub x and f sub y both exist. Now, if they don't exist, you cannot calculate the gradient. Okay? If f sub x or f sub y or both didn't exist, that means you've got a vertical line there, and you can't calculate the gradient there. Or they just don't exist. Okay? Then the gradient of f, and notice how they bolded the word gradient, denoted by, and this is an upside down delta. Now I've heard sometimes people refer to that as a del, D-E-L. This book uses the term grad, G-R-A-D. But notice this is sort of bold looking. That is certainly bold. Gradient is bold. The boldness, oh, there's it. Red is del F. So that is del. Okay? Del F. Okay? It's a vector. Okay? That implies vector. F is a scalar function. Del is a vector that comes from a scalar function. What you do with it, you take the partial of F with respect to x. That will be the component in the I direction, and the partial of F with respect to y will be the component in the j direction. Symbol del F is read del F. Another notation for gradient is given by grad F. Okay, same type thing. That means gradient of F. And the figure down here says, note that for each xy, the gradient del F of xy is a vector in the plane, not a vector in space. Okay? It's a vector in the plane down here, not a vector somewhere up here in space. It's a vector on that plane. Because all it has is an x and y component, it doesn't have a z component. Okay. Now, we're going to get to what it means in a bit, but this would be it right there. The gradient of f is a vector in the xy plane, and we'll tell a little bit more about it in just a minute. Okay? The components of it is a partial of f with respect to x in the I direction, partial of f with respect to y in the j direction. So here's example 3. It didn't tell you anything else about it. We'll get to it in a bit. Find the gradient of f, where f is y log x plus xy squared at the point 1, 2. Time out. Let's make sure the point 1, 2 is valid here. Y is equal to 2. X equal 1. What's log of 1? Zero, yes, the log of 1 is 0, so that is 0, and when x is 1 and y is 2, x times y squared would be 4, so this would be 4. So we're talking about the point 1, 2, 4, where 4 is the y value at that point. Okay, that didn't prove anything, but just shows you where you're talking about. Now, my nose is itching like crazy. How do we find the gradient of that f? What you reckon we're going to do? Anybody?
So we made sure that f of y and f of x.
Yes, we have to take the partial of f with respect to x at xy. And what's that? Y over x. Okay? Plus. No. With respect to x. Y is treated as a constant, so y squared is like a constant. So just a y squared. Right? Okay. Next. Partial of f with respect to y at xy would be, second? No, partial with respect to y. It means you treat x as if it's a constant. If x is a constant, then log x is a constant. Just the derivative of y, of constant times y, would be log x. Right? Okay? Plus 2xy. Perfect. Now, we don't just want them anywhere, we want them at that point. So f sub x at 1, 2 would be what?
So that's 1/2 plus.
What? I couldn't hear what you said.
1/2. No. I'm sorry. 2.
2
2
plus 4 equals 6. Okay. And f sub y at 1, 2 would be, right? And 4. Okay. Which is equal to 4. Okay. So what is del? And since I can't write a del bold, I put a vector symbol over it to remind me that is a vector of the function f. And we'll first write it at xy is, with respect to x, which we had as y over x plus y squared times I okay, 2xy. Goodness gracious. My hearing's bad, but also my motor skills are not great. 2xy. Okay. That last sneeze I had a while back just really messed with my head. Goodness gracious. Okay. And that will be the j component. Okay. So at the point, so del at the point f of 1, 2, and we've already calculated that, that would be 6i, because we calculated it up here, plus 4j. 6I plus 4J. Good for them. They got it right too. Okay. All right. Any questions on how we did it? All right, let me clear this. And let's see how they did it. All right, here's 7. All right, let me, sorry I have to do this to everyone who comes in, but I want everyone to hear it anyway, because you might not go back and listen to the first part of the things that you were here for most of it. Back in June, sometime around June 12th or so, Governor Ivey came out with a proclamation that the 5th of July would be part of the 4th of July weekend. So she made it a state holiday as well. I didn't know that. I didn't pay any attention. I wasn't listening. I didn't know it. But last Thursday, one of the secretaries on the Birmingham campus, I had to go over there to take care of some paperwork, said, "Did you hear we're only working half day on Wednesday?" I said, "No, I hadn't heard that." She said, "Yeah, the governor gave us a Friday off, and since we aren't working Friday, we'll have part of Wednesday off." Well, I hadn't heard that officially and didn't hear it over the weekend. And as of this morning, still hadn't seen anything of it. So I checked with some few people, and no one else had heard either. Sorry. I had a bunch of sneezing earlier, and now I've got so much drainage I can hardly handle it. But anyway, then after my first class was over with, and before my second one began, which began at 11:30, I needed to tell them something. So I went down to check to see if any news had come in. No one had heard anything. So I started calling. I called my boss, got his voicemail. I called the secretary who I heard it from, got her voicemail. I tried the dean, who's my boss's boss, got her voicemail. Then I tried the executive vice president, and her secretary picked up, said they hadn't heard anything. And they said, "We never know until the day of it." And then we found out we have a half day off. I said, "Well, I've got class, and I need to tell them whether to come Wednesday or not." "Oh, well, we don't know. Won't know until Wednesday." So then I called the vice president's office. His secretary did pick up, and I asked, and she said, and this is 11:30-ish, you know, and she said, "Oh, it hasn't been decided yet." I said, "Well, look, I've got a class in the room waiting for class. I need to tell them whether they need to come on Wednesday or not, because if school's closed at 12, why would they come at 11:30? And she said, "Well, I'll try to find out. I'll give you a call." I said, "Well, I'm going to be in class. I won't get the call." "Well, I'll send you an email." "Oh, I'll just have someone come tell you." Okay. So sure enough, 12:45, okay, an hour and 15 minutes into class, and sometime after that, here came this, that because Governor Ivey is recognizing July 5th as part of the July 4th holiday, college will close on Wednesday, July 3rd at 12 o'clock noon. So afternoon, there will be no classes, so this class will not meet on Wednesday at all. My 11:30 class, I told them I'd be here at 11:30. If they wanted to meet, we'd have 30 minutes of class, but that'll be it. Of the ones who are here, none of them said they were coming back Wednesday, but I'll be here Wednesday, at least until 12 noon. Okay? Are any of you taking classes with A&M on the Lawson campus? No. Okay. Well, they don't know about that, how A&M is doing, but Lawson classes will be through at 12 o'clock noon, and the rest of the day will be canceled. And then they say in here, and all Saturday classes will be canceled. we don't have any Friday or Saturday classes in the summertime, so I don't know where they're getting this. The administrators have absolutely no idea what's going on. It seems like down here on the line. So anyway, that's what we got. So no class Wednesdays. Sorry about that. Get over it. Okay. Yeah. Okay. Good for you. All right. So here we have the functions. There's your f. You did the partial with respect to x, partial with respect to y. So your gradient, that's called del f or grad f of xy, is f sub xy I plus f sub y xy j. And then plugging in what those are, it's minus y over x plus y squared I plus log x plus 2xyj. At the point 1, 2, we plug that value in, and we get the gradient of f, or del f, grad f at 1, 2 would be 2 over 1 plus 2 squared I. So that would be 5i. Is that what we got? No, 6i. Oh, 2 over 1, 2 plus 4. 6i plus log 1 is 0. Plus 2 times 1 times 2, that would be 4j. Yeah, and that's what we got. 6i plus 4j. Any questions? Okay. Now, because the gradient of f is a vector, we can write the directional derivative of f in the direction of u. Directional derivative of f in the direction of u as if you think about this, it's partial of f with respect to x, I, plus partial of y with respect to partial of f with respect to y, j. That's the gradient of f. Dot that with the component vector u, cosine theta I plus sine theta j, if that's what we know it as. And that gives us that directional derivative, f sub x times cosine plus f of y times sine. That is a scalar quantity, which is the slope you could think of the tangent line that's in the direction of that vector u. In other words, the directional derivative is the dot product of the gradient vector and the direction vector. Okay, the unit direction vector. Remember, the direction vector is always the unit vector. Even though they sometimes give it to you as some other vector, you have to get it in the unit vector form. Okay, the alternative form of the directional derivative, then the f is the differentiable function of x and y. This board is in terrible shape. Then the directional derivative of f in the direction of the unit vector u is directional derivative in the direction of u, unit vector u, of f of xy, of this function f of xy, is del fy, del f at xy, dotted with that unit vector u. Now, if they give you that as a vector v that's not a unit vector, first find this unit vector by dividing by its magnitude, then do the dot product. Or you can do the dot product and then divide by the magnitude. That's just another way of expressing it. So, find the directional derivative of this function f of xy, which is 3x squared minus 2y squared, at the point negative 3/4, 0, in the direction from p, which is minus 3/4, 0, interesting, to q, which is at 0, 1. So you're finding it in the direction of the point here. This is where you're going to calculate it, but you're going to do it in the direction from that point to the point 0, 1. Okay? So we got a couple things we got to do first. Tell me what you got to do. Okay? So you want f sub x. And what would that be? 6x, got it. And partial of F with respect to y minus 4y. Perfect. What do you do with that? Say again?
Plug it into the direction of the formula.
Okay. Okay. Tell me what to write down. Okay. F sub x at xy. Is that what you said? No. Okay. I'm sorry. I have a hard time hearing.
So D.
Oh, D. Okay. D sub U of F of xy
equals 6x.
okay, 6x say again.
Do we have to find the unit vector?
Yes, we do. Well, even before that, we have to find the vector.
Right.
Okay, what vector are we talking about? I'll write it PQ. That's another way to write a vector. Initial point P, so it says from P to Q, so Q is the terminal point. So we write it from P to Q, that's vector P to Q. What would that be? We are, but we got to get the components first. Okay? Don't know what you mean by that. Okay? To get the components from this point to this point, you do x2 minus x1 is the x component, y2 minus y1 is the y component. Yeah, but that's not what we're doing. We're just finding the components of the vector, the PQ. So what would that be? Right. Okay, it's 0 minus a negative 3/4, so that would be 3/4, comma, 1. Okay, there's the vector from negative 3/4 to 0 to 0, 1. We also need to find its magnitude of PQ. And what would that be? It's the square root of 9 over 16 plus 1. And that would be, that's right, that is 16 over 16. Isn't that 1? Okay, so that would be 9 over 16. Right, and that would be 5/4. There's the magnitude. So what do we do with that? The unit vector in the direction of PQ would then be well, no, okay.
I'm sorry, we're dividing.
Yes. Right. So it'd be this vector, goodness gracious. Okay. This vector, 3/4, 1, divided by 5/4, which is the same as 4/5 multiplying by the reciprocal times 3/4, 1, which would be, okay, 12 over 20, but you could just divide out the 4s and do it 3 over 5, comma, 4/5. Okay. Now, just pause a moment and ask, is that indeed a unit vector? Square this one, you get 9/25 plus 16/25 is 25/25, magnitude 1. Perfect. Okay. So, I got so far as writing 6x. Okay, you don't need that anymore. Yeah. Times 3/5. Okay. Now, oh yeah, I forgot my y. Okay, I'll put it in. Now we don't just plug in those, we plug in your x, y values too. And here's the point you're talking about. So this will be so 6 times -3/4 times 3/5 plus, goodness gracious, my eyes are stinging, -4 times 4/5 times 0. Oh, so what's this? Okay, I couldn't hear all that. Okay. Okay, 27 over, if I cancel 2 into this and make a 3, 2 into that would be a 2 over 10, which would be minus 2.7. Okay. So the directional derivative in direction of that vector here, PQ, from the point 3/4 0 would be negative 2.7. This is pretty steep downhill, and let's see if we can see a picture of it. Yes, they have one here, negative 27/10. That's what we got, or negative 2.7. And let's see if we can figure that one out from the graph here. Okay, so in the xy plane, here's the vector negative 3/4, no, 3/4 1. 3/4 on x, and oh goodness gracious, 1 on w, 1 on drawing it in the straight. Excuse me. They're drawing at negative 3/4 0, so that's negative 3/4 x 0 y. That's the initial point, going out to the point 0 1, which is right here. So there's your vector there. But you're doing it up here, so extend that upward, and boy, there it is, a very steep negative slope, negative 2.7. That blue line looks reasonable for that component vector. The one they showed here just looks nothing like. I don't know. I don't know where they got that blue line there, but it's totally whacked out. Okay, but that one looks pretty good. Okay. All right, that was example 4. Now, let's see how they did it. Let me erase my chicken scratch. Okay. Because the partials of alpha are continuous, they are, alpha is differentiable, and you can apply the theorem 1310. Okay. Now, the vector in the specified direction is, and this is exactly how we did it, I even named it the same way, from P to Q would be, this is, the Q was 0, P was 0, 1, and Q was 3/4. No. P was 3/4 0, and Q was 0, 1. Okay. So it's from P to Q, so it would be the Q value minus the P value. So this would be 0 minus 3/4, or positive 3/4 I, and then 1 minus a 0 on the J, so that would be 1J. So there is the vector in the specified direction, 3/4 I plus J. The unit vector in that direction would then be that vector, divided by the magnitude of the vector. Now remember, the vector itself is 3/4 I plus J. And the magnitude of this vector here was, they don't show it here, they didn't do the calculations for it, but it was 4/5. No.
It was 5/4.
5/4, yeah, 5/4, because it was this vector here. Yeah, that'd be 9/16 plus 16/16 would be seems like one of these should be a minus sign, but I don't guess so. Yeah. Well, that would be 9/16 plus 16/16. That would be, 25/16, which is 5/4. Yeah, that's it. Okay. My head wasn't doing the calculations right. So that would be 5/4. So you take that vector we had and divide by 5/4. And dividing by 5/4 is the same as multiplying by 4/5. The 4's go out and you get 3/5 I plus 4/5 J. Okay? And that sure enough is a unit vector then. And because del F to the gradient of F is the partial F with respect to X I plus partial Y with respect to Yj, and that was 6X I minus 4, 4Yj. At this point, then that would be 6 times 3/4, and that would be minus 9/2 I, and then minus 9 times 0 is, minus 4 times 0 is 0, 0J, so it would just be the gradient vector is only in the minus I direction, minus 9/2, and then you dot that with your, they're writing it as del F again, and that would be negative 9/2 I plus 0J, dotted with 3/5 I plus 4/5 J, and that would be 9 times 9 over okay. 9/2 times this, that'd be 27/9 plus 0. 27/10. 27/10 plus 0, which would be negative 27/10. And here's the picture as I was trying to hold up before, I wish I hadn't done it. Here is the component vector P from P to Q. P was minus 3/4 0, minus 3/4 of X, 0 Y, going out to 0, 1, nothing on x, 1 on y. Draw the vector from E to Q on the xy plane, and that's the direction you want the directional derivative in. Here's the point where you want to take it, and in that direction, boy, that's steep downhill, and sure enough, it's about negative 2.7. See, this does seem to be in the direction of that, whereas the last one, it would seem to be perpendicular to it, so I don't know where that came from. Okay. How are we doing time-wise? We've got about 5 minutes. So, applications of the gradient. This is top of page 924. These are some properties of the gradient. So let f be a differentiable function at the point xy. Then if the del f, or gradient of f of xy, is equal to 0. Now notice this is a bold 0, that's the 0 vector. Okay? Okay? If that's the 0 vector, in other words, the gradient is 0. It doesn't have a gradient. 0x plus 0y, you know. 0I plus 0j, you know. Then the directional derivative in that direction would be this dotted with the unit vector u, but it doesn't matter what u you put out there. If you dot 0, 0 with it, you're going to get 0. This is a scalar number 0 because the directional derivative of a scalar, the gradient of a vector of a function is a vector. So that's why it's a bold 0 there. Now, the direction of the maximum increase in f of f is given by the graph, the gradient of f, del f. The maximum value of d sub u, that's the directional derivative in the direction of that unit vector u, is the direction of maximum increase would then be your magnitude of that gradient vector. Okay. The direction of minimum increase in f is given by the opposite of del u. The direction will be the opposite of del u, del f of xy, and its minimum value would then be the negative of that. Okay? All right. Here is example 5, because we just did example 4. The temperature in degrees Celsius on the surface of a metal plate, and I believe this is maybe Newton's law of heat, okay, is equal to 20 degrees, which is the initial condition. That means room temperature. So degrees Celsius, 20 degrees Celsius is basically room temperature. So T of xy, temperature is x and y, would be 20 minus 4x squared minus y squared, where x and y are measured in centimeters. What direction from 2, -3 does the temperature increase most rapidly, and what is the rate of the increase? Okay. What direction from 2, -3 does the temperature increase most rapidly? How are we going to get that? What gives us the direction of maximum increase? A little louder. It's certainly a good step, but here's why. Because the direction of maximum increase of f is the gradient of f, which you get from taking the partial of f with respect to x, I, plus the partial of f with respect to y, j. Okay? That's the direction of the maximum increase would be in the direction of del f. So, here we got t, so it's not f, but t. We're going to do del t, okay, is equal to anybody help me? Anybody? What's up?
So you said we don't need to take the partial derivative?
Yes.
Okay, so the partial with respect to x would be
Negative 8x. Right. And yeah, the rest of them are constants when you're taking the partial with respect to that. But this is a vector, so that will be in the I direction. Negative 2y in the j direction. Okay. So the maximum increase is back that way in x and back that way in y. So somewhere back that way. Now, from the point to negative 3, in what direction from to negative 3 does the temperature increase most rapidly? So what we have to do, we know this is direction in general where it increases most rapidly, but now we plug in from to 3, so your del T is equal to minus that would be negative 16. Goodness gracious, my pen is dragging. Negative, goodness gracious, these marks are, I guess I point to things and leave marks where I don't mean to. Goodness gracious. Okay. Whew. Negative 16i negative what, 6? No, positive 6. J. Okay. All right. That's the direction from 2, 3 where the temperature increases the most rapidly. Okay? Now it says, what is the rate of increase? All right. What gives you the rate of increase? The maximum value, that's the rate of it, is the magnitude of your del F. So what would be its magnitude? Okay. Wait a minute. Okay. I squared the first one. I just wrote it as a square on the first one and squared the second one. So if you're following that, it's the square root of what? 292. 292. Is that the total? Okay, 292. Take the square root of that, and what would it be?
273.
Say again?
You want in decimal? You want in decimal form?
Yeah.
So 17.08.
Yeah, okay, that sounds reasonable. 17.08. That's probably more digits than we need, but that would be for some reason, the units are not making a lot of sense here. X and Y are measured in centimeters. All right, I think I would say centimeters per second, but I'm having trouble. That's usually a rate of increase, but I don't see a time in here anywhere. Oh, no. Okay. It's not centimeters per second. This is degrees Celsius per centimeter. Okay. It's the X and Y are measured in centimeter. This is temperature, so your numerator part is the temperature. Your denominator part is your is the you do it with respect to X, then with respect to Y. Both of those are in centimeters, so it'd be change of temperature per centimeter. So that does make sense. 17.8 degrees. They put 0.09. They just rounded differently from you. 0.09. Degrees centimeters per centimeter. Degrees centigrade, or degrees Celsius per centimeter. I'll get it right in a minute. Okay. Now, and that's exactly what we got here. So the direction of the maximum increase is in the direction of that del T. The rate at which it changes is degrees per centimeter. Okay. What you think about taking a break now? I certainly need something to drink. My throat is so dry. Huh? Yeah. Isn't it about time? Yeah, and we go till 5:30, so it's about midway. So let's take a quick break here. So I think it has to be allergies. All right, we are recording again. Yeah. So we just found it's 17 point, the maximum rate of increase, and this is the part that sort of threw me. When you do the gradient, remember it's such a nice shorthand to do f sub x and f sub y. In this case, it's actually t sub x and t sub y. But if you think about what, yeah. Oh, yeah, I'm sorry. Come on, speak up. I may not see you. Okay. But it's helpful to remember what that stands for. This is partial of t with respect to x, and this is partial of t with respect to y, and that's where our units come from. Temperature is in degrees Celsius, and this is in, what was it, centimeters, wasn't it? Yeah, centimeters. And this was degrees Celsius in per centimeter. So when you add them together, it's degrees Celsius per centimeter. Because here you're squaring them and then taking the square root. Okay. So that's where the units come from. All right. Now, that's on that particular spot. It could be that someplace later you're going to have a maximum increase of something else. And let's see. Oh, they show this one. So why am I holding up the book? Let me erase this. Sorry, my throat is going on me. All right, the gradient is del T. That's the gradient of the temperature for, at the point here. And that's the change of temperature per change of X. That's what I was just talking about before. I plus the change of temperature per change of Y, J, and that would be minus 8xi minus 2yj. Okay? Then you plug in the values at 2, negative 3, and that gives you negative 16i plus 6j. I think we got the plus 6 right, didn't we? I don't remember now. Okay? And so this gives you the direction of the greatest increase. The rate of increase is the magnitude of that, which would be square root of 256 plus 36, which is our square root of 292, and that is what you had, right? And that gave us your thing. Now, notice here, eyes are stinging. Okay, your maximum rate of increase. They've shown here the level curves. If you picture this, there's your function, and that's basically an elliptic paraboloid. Okay, where t is your single variable and the other two are squared. Okay, and this would be 20 at the center here, and then these curves or whatever they come out being. Okay, and here we are at 2 on x and negative 3 on y. That would be 2, yeah, 2x, negative 3 on y. They don't, yeah, there's 1, 2, 3, yeah, they showed here. Okay, now, we haven't gotten here yet, but this is true. These are the level curves, so these are ellipses. Okay, your y-axis being the major axis, the x-axis, the minor axis. And at this point, the direction of maximum increase is here for a short time at this point. Now, here's what we haven't gotten to yet. This is always a right angle here. Pretty close to a right angle there, getting a little less there, but always perpendicular to the tangent here. Okay? We haven't gotten there yet, but that's what we're doing. Okay? That's the direction of maximum increase. But you see, once you leave this point, then when you get here, it's going to be a little bit tilted this way. When you get here, it's going to be a lot tilted that way. When you get up here, it's going to be tilted, that way even more and on. But you're going toward the center. So wherever you're going now, sorry. This really is bothering me. This is the eye I had operation on, the cataract removed. It is just burning up when I look in a certain direction. I hope it's just an eyelash column there or something, but it's bothersome. Okay, so that's the direction, and this is the rate of increase at that point. How much the temperature is changing. This is increasing as you go from here to here to here to here to here. So it's a change of increase per unit, and the square root of this thing squared, this would be per unit centimeter. So per square centimeter, and that's what, I mean per centimeter, as you're going. Because the length of that vector is in centimeters. So that would be represent what we've got going here, and that is square root of 292, which is about 17.09 degrees per centimeter. Now you don't have 4 significant digits of precision there, so I don't know. I would have just said about 17 degrees per centimeter. Okay. Now, they skip example 6. So let's go back and do example. Well, they don't give us much room, do they? I guess we have more room on this. Well, there we have the most room. So let's do example 6. A heat-seeking particle is located at a point of 2, -3. Same place we had before. 2, -3. A heat-seeking particle on a metal plate whose temperature is given by exactly that same function. I wish I'd have kept it up there. Okay, in fact, let's go back and use that. Okay, there's the function, and we got the same point. Okay, find the path of the particle as it continuously moves in the direction of maximum increase. Okay, now this time we're starting at a given point, but we're not going to we want to find the path of the particle as it continually moves in the direction. Okay, so everything we did before, this time I'm going to write it the way partial f with respect of t with respect to x is the -8x, and partial of t with respect to y is the -2y. Okay? Okay. Man, my eyes are burning. Okay. Now, the path we're going to talk about is r of x and y, okay, which will be some x of ti plus y of tj, okay, because it's how much is changing in that direction as a function of time, plus how far it's changing in the y direction as a function of time. So the tangent vector at each point, xy, will be r prime of xy, which would be here dx dt I plus dy dt j. Okay? Now, because the particle seeks the maximum temperature increase, your del T, just like we did before, is going to be this thing here, minus 8x in the I direction, minus 2y in the j direction. I can't write. In the j direction. Okay? Now, that would be at each point on the path. So that's your gradient vector at each point. Now, what you need these values here and these values here are the same at every xy, okay? So we can what they say here is minus 8x. That's the value of del t, the gradient of t, and that has, sorry, to be proportional to your dx dt. Okay? Because this is the rate of increase of your function. This is position of the function, and this is how the position is changing. In generic terms, that's how we actually know it is, so that has to be some proportional to this quantity here. And goodness, my eyes are stinging like crazy. Minus 2y has to be that same proportional times your dy dt. Okay? In other words, it has to be moving at the same rate. Okay? Now, but k depends somewhat on the time. Okay? And if we get time out of the picture here, so this is a bit bizarre. It said if we let this ratio be constant, then that means we divide by dx. So you have well, the reciprocal of that is constant. This really sounds a little bizarre, but it is indeed true. I don't know if you remember, when we write it in differential form, you want the dt's to be by themselves, so you want them in the numerator. So you have to do the reciprocal of this. In other words, dt over k, in both cases, dt over k, in this case it's dx over, or minus 8x, and in this case it's minus dy over 2y. Okay. Now, and if these two are equal to each other, that means that dx over minus dx over 8x equal minus dy over 2y. Now, remember what we're looking for, find the path of particle. Okay. Well, we're getting there. If we write this as wow. What they do next is solve a differential equation without telling you how you solve differential equations. There was a chapter back there, chapter 9, I believe it was, or somewhere back there, that was on differential equations, but typically we don't cover that here because differential equation comes after this. But they tell us the solution of that differential equation, that one right there, happens to be x is equal to some constant c times y to the 4th power. Now, let me show you how they get that. They don't explain it here, but if you integrate this and integrate that, notice I took out the 1/8 here and the 1/2 there and the minus signs here. What you have here is negative 1/8 times the log of x, because the antiderivative of dx over x is log x, is equal to minus 1/2 times the log of y. Okay? Now multiply both sides by -8, and you get log x is equal to positive 4 times the log of y. Okay? Principle of logarithm, 4 times the log of a number is the same as the log of that number to the 4th power. So this gives you log x is equal to log y to the 4th y to the 4th power. And if you do an exponential of both sides, that undoes the logarithm, you get x is equal to, and what we have here is a constant here, because it's an indefinite integral, and do an e to the c here. So what we have here is x is equal to and before you combine those, before you take the log of both sides, wait, I hit the wrong button. Okay. Let's hold off on doing that for just a minute. If you have e to the log y 4th, which, okay, and e to the c, you can then combine those, multiply those together, and basically this becomes e to the, let's make that log c. That will make it a lot better, okay? So we'll have okay. They shouldn't be doing differential equations here anyway, but anyway, what we have here is x is equal to, combine those together and you get c y to the 4th, and that's where they get this, okay? That's, yeah, why they say that's the differential equation. Because the particle starts at the point 2, -3, we knew it started there, we can go back and plug in. So when x equal 2, that's c times -3 to the 4th. Okay? Okay? So this will be 2 is equal to c times, and -3 to the 4th power is positive 81, right? Okay? So c is equal to 2/81. So then you can go back and put that in, and you have x is equal to 2/81 y to the 4th power. Okay. And that's going to be the path that it takes. That's x as a function of y. And here, oh, no, they don't show it. So let me show it here. That equation there is here. You start here, and again, you're perpendicular here, perpendicular there, perpendicular there, perpendicular there, perpendicular there. You see, as you're coming up, you're going not straight toward it, but you're going the path, and this happens to be the path, even though it's a curved path, that's the path of shortest distance to get from here to there, because you're going maximum temperature gradient as you go. And sure enough, that's true. And this, if you think about it, that looks like half of a quartic function. You know, it's flat here and curves up there pretty sharply. And that's exactly what you got. I can't hold it there any longer. And that's the path that's presented here. Now, this problem took you way beyond what we've done so far in the course. Now, sure, in the book, they show you how to do differential equations, but that's a different course. Okay, so I usually skip that one. Okay. Now, I think that finishes that part. So let's now go to theorem. And so you see if you drew that curve in here, that would be, I can't draw well, but it would be something like that. Okay. And then if it had a mirror on the other side, it would go there, but of course that doesn't make sense physically. So sure enough, that's how it gets to the maximum point. Okay. Here's theorem 1312. The gradient is normal to the level curves. I told you this was coming, and that's exactly what we see there. Remember this figure I just showed? This is perpendicular to that curve. That's the only one that's perpendicular to here. But then when you get to this point here, this one's perpendicular there, that one's perpendicular there, that one's perpendicular there, that one's perpendicular there, and then you land right on top of that. Okay? So, if f is a differentiable function at x0, y0, and del f at x0, y0 is not the zero vector, okay, then del f, which is the gradient of f at x0, y0, is normal to the level curve through that point. So whatever your level curve is there, your gradient is always perpendicular to it. Now, here's example 7. But before we do example 7, I wanted to ask you to flash back. Remember when we talked about isobars on the weather map, and you have the high pressure in the center, okay, and you have the level curves around it were all at the same barometric pressure. The wind, if this is high pressure in here, the wind is flowing in that direction. If it's low pressure, it's flowing in this direction. I believe that's correct. And so they're always going in. Now, where those level curves are closest together, greatest wind speed, because there's the largest gradient there. Where they're far apart, that's a very gentle breeze blowing in, but it always blows in perpendicular to that. All the other isobars, isoclines, if you've got a topographic map and you the steepest increase is perpendicular to the level curve. If you go along the level curve, you're not changing elevation at all, okay? So you're at the same elevation. There's no steepness at all. But when you go perpendicular to it, that's the maximum steepness, uphill or downhill, depending on which way you're going. Okay, and the magnitude of that is that. So that's what it's talking about here. So here it says, sketch the level curve corresponding to c equals 0 for the function given by, and I'll tell you what c is right now, given by f of xy is equal to y minus sine x, and find a normal vector at several points on the curve. Okay. Level curves corresponding to c is equal to 0. Okay. So, what do you think we need to do first? What seems to be a good idea? Second? Yes, let's take the f's of x, of xy, and what would that be? That's negative cosine x, okay? And what's your f sub y? Is equal to 1, okay? That's it, okay? So sketch the level curve corresponding to c is equal to 0 for the function given by that, okay? Now this is, I guess basically done like the previous example, okay? The path of the heat-seeking particle, okay? So oh, now I see what they mean by C. Remember, what this means is this function has various values, right? So when C is equal to 0, this thing is equal to 0. So that's where we start here. Y is equal to, y minus sine x is equal to 0. That's the value C. That's the Z value, F value, where that's equal to 0. Just set it equal to 0. Well, what that implies is that y is equal to sine x, right? Now, what are the values of well, that's, I guess the better way to say it is that is a function of, that is a description of your sine curve, okay? Yeah, I'm not going to draw the whole thing, but that's your sine curve. Now, if this is the x-axis, this is the y-axis. If we take that and lay it down, okay, and make that a cylinder, you know, then the z is going up and down from there. So let me actually change that. And I can't draw this worth a toot, so I'll just do the best I can. This is your y direction, this is your x direction, and this is your z direction. Okay? Now, as you're increasing x, it's going up and down, up, and this is going negative x, negative y. So this is going like this, like this. Well, extend this up, all these up, parallel to the z-axis, and you've got a curve that is winding around. A sheet, a cylinder that winds around like that following the z-axis. I mean, that. Now their picture is a little, they did more of an isometric drawing, so you see it a little differently, but that's basically what you've got going here. Okay, and when C is equal to 0, that's exactly what you got. Now, sketch the level curve we just did corresponding to C is equal to 0. And this could be the level curve here, that one down there. Okay? Now, says find a normal vector at several points through the curve. Now, a normal vector is going to be one that is this way, that way, this way. Those are the normal vectors, okay? Meaning they're perpendicular, normal to the level curve. Well, that's going to be the gradient, because we just learned from the previous thing that if f is differentiable, then the gradient of f is normal to the level curve, okay? And if that's the level curve we're talking about, then this will be. So what you said was right. We want to find the gradient, so that would be del f, and that's a vector, okay, is equal to minus cosine x I plus j. Okay? Now, when x is a half pi, like right there, then this is going to be in the minus cosine of this is 0, so it doesn't have an x component, so it has a unit vector j in the that shows it in the minus y direction. Why is that? Okay. Oh, it's pointing outward. Sorry. It's pointing in this direction. The normal is pointing in that direction. Okay. I can't tell you exactly why it is, but usually they point toward the inside, but they have them pointing to the outside. So it's pointing outward. So that's a positive J. Yuck, I erased everything. I sure didn't mean to do that. So this is, okay, right there is the tangent. So the normal vector would be here, and that needs to be perpendicular with parallel to the y-axis, which it kind of is. Okay. And I don't know why it started doing this morning, just every now and then shutting down and going through all sorts of things and coming back. I don't know what it's doing. My lights are up here kind of flashing and strobing, but I don't know what's going on with it. Okay. So, in general, that is your gradient vector, so that is always going to be perpendicular to your level curve at any value you put in there. So, and this is a function of x and y, so at any point you put in there, such as this point right here will be at pi halves 1. So del f at pi halves 1 is going to be cosine of pi halves is 0. So it'd be 0i plus j. So it's just going to be j. And sure enough, this is in the perpendicular direction there. And any value you put in there at negative pi 0, negative pi 0, right there, at that point, what is your normal curve? Del f at negative pi 0, you're going to be minus cosine of negative pi. If you think about it, cosine starts at this, it's negative 1 there, so negative 1 is going positive 1, so plus I plus j. The plus j is always there, okay? So this one's going to be plus 1 in the I direction, plus 1 in the j direction, and sure enough, it's going to be exactly perpendicular to that curve there, however you draw that. When they do del f, and they just go down and do a whole bunch of them, and sure enough, they're all perpendicular to the curve at those values, okay? And, oh, they're going to show this. I forgot. Let's take mine off of here so you don't have to look at my ugly drawing. Let's do theirs. Now, they did the curve in a different orientation. They did the x out here and y here. And if you look down at it, you see it's a sine curve that goes like this, like this. They really don't have this is pi halves, should be about 2/3 of a unit this way, and yet that's 1 unit this way. So they have a really flattened curve here. That's 1 unit, and this is 1 unit here. So I wish they had drawn it better so you could have a little more of a load here, but they didn't. They drew it this way. Okay, that's the surface given by f of x is equal to y minus sine x. When c is equal to 0, this is the level curve down there. Okay, when you're not up or down at all, your z is equal to 0. Okay, because the gradient is going to be minus cosine xi plus j, you can use theorem to conclude 1312 to conclude that f of xy is normal to level curve at every point xy. So they do a bunch of the points at minus pi 0. You know that's on that curve, and there you're at I plus j. Okay, at negative 2/3 pi, which would then be the minus cosine of that would be 1/2, and the y component would be this. Who cares? I mean, this is always plus 1. Okay, so you'd be minus or positive 1/2 I plus j. The next one at negative pi halves, the cosine is 0 there. You would just be a plus j. Now let's remind ourselves to look at that one. That's pretty easy to do. At minus pi thirds, minus 3 square root of 3 over 2. Really doesn't matter what the second one is. You're minus 1/2 I plus j. And at 0, 0, you're minus 1 j, because it's minus cosine, which is minus 1 I plus j. Always a plus j. Okay? And then when you're at 2/3 minus cosine of pi thirds is 1/2, minus that is minus 1/2 I plus j. Pi halves, that's the one we did, 1, I think that's the one we did, yeah, that would be plus j. Okay, and you go on and on and on. 2/3 pi, you'd be at minus, cosine is minus 1/2, but minus cosine would be 1/2 I plus j, and at pi, it would be minus 1 plus j. Okay, let's think of these on the curve here. Okay, and these are always pointing on the upside of the curve. That's why I was messing up with mine. Here's that first one that was before, minus, no, positive I, positive j in this direction. 1/2 I plus j. See, your j component is always 1 unit. They don't have this quite long enough. It should be a little bit longer. No, maybe not. You got the angle there, so that's okay. And this one is exactly j plus j. I said that's the one to pay attention to in that. This is minus 1/2 on the x plus j on the y. Okay. This is minus 1x minus 1j. Oh, minus I. So that would be, if this is 1.5, that would be about 1. So sure enough. Notice the length value varies, but the j component always stays the same. Here, 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 here. J component is always 1 upward. And that's why it's always pointing upward, because the j component is always up. Okay? And over here, but notice perpendicular, 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 perpendicular. All these are perpendicular to the curve, which they've got to be. That's a level curve. Those are the normal vectors to the curve. Okay. Now, yeah, I think we beat that one to death. Now, functions of 3 variables. We've been dealing with 2 variables so far. Let's do functions of 3 variables. Whoa, okay. Directional derivatives and gradients for 3 variables. If alpha is a function of x, y, and z, all 3 independent variables, that's what we should be saying there, with continuous first and partial derivatives, that's necessary. The directional derivative of f in the direction of the unit vector, and the unit vector has to have 3 dimensions as well, ai plus bj plus ck. Remember, this is the unit vector though, so these are all numbers less than 1, less than or equal to 1, and if any one of them is equal to 1, the other 2 have to be 0. Okay, and if any one is not 0, none of the others, they all have to be less than 1. Okay, and the directional derivative is given by the derivative in the direction of u. Now remember, it's a scalar quantity, even though it's in the direction of u, of f of x, y, z is sum this a times the partial of f with respect to x at x, y, z, plus this b times the partial y at x, y, z, plus this c at the times the, remember, it's the u dot gradient. Okay? So the gradient is defined as partial of f with respect to x at x, y, z, I, partial of y, f with respect to y, x, y, z, j, partial of f with respect to z, x, y, z, k. So you see these components are the components of your gradient vector. These are the components of the unit vector. So the dot product of those 2 produces that. So the properties of the gradient are as follows. The directional derivative is the gradient dotted with the u vector. Here they wrote it as if it's u dotted with gradient. It doesn't matter. A dot product is commutative. Cross products are not. Dot products are. Okay? And if the gradient of f is the 0 vector, then the directional derivative is 0 everywhere. For any vector you happen to have, unit vector u, it's always going to be 0. The direction of maximum increase of f is given by the gradient of f of x, y, z. That, remember, is a vector quantity, and the maximum value of the directional derivative is then going to be the magnitude of that. The maximum increase is that, and the maximum value is that of this is the magnitude of that gradient vector. The direction of the minimum increase is the minus f, and the minimum value would be minus the thing. That would always be, if the maximum increase is going up there, the minimum has to be here. Same magnitude, okay, but opposite direction, okay? So that's why the magnitudes are exactly the same. Only one's going uphill, one downhill, and the direction of maximum increase is going to be that vector here as maximum decrease, that vector there. I mean, it almost has to be that way. Okay. So here's example 8. Find the gradient vector for this function. Alpha of x, y, z is equal to x squared plus y squared minus 4z. And find the direction of maximum increase of f at the point 2 minus 1, 1. So what are we going to have to do first? Take the partial derivatives. So partial of f with respect to x is 2x. And partial of f with respect to y is 2y. And the partial of f with respect to z, negative 4. So what would be your gradient? That's a vector. That's a function of x, y, z would be it'd be 2x in the I direction plus 2y in the j direction minus 4 in the k direction. It's these components of the unit vectors in the corresponding thing, okay? X is in X direction, Y is in Y. Okay? Now, if you want you found this. That's the first part. Done. For that function. Then find the direction of maximum increase at this point. So guess what we're going to do? It's going to be the gradient at 2 minus 1, 1. So what will that be? For I minus 2j negative 4k. That doesn't change. It's going to be negative 4k no matter what your third point is, because there's no z dependence on your gradient vector. Okay? So there's the direction of maximum increase of f at that point. That direction. Your gradient vector at that point. Now, sometimes when they say the direction of maximum increase, they mean the unit vector direction. So if that's what they meant, you would just divide by its magnitude. I don't think that's what they mean here. No. They just have that. So yeah, that's it. Now this, by the way, that shape there is the shape itself, just the function f, is a elliptic paraboloid, okay? Because your z is to the first power and your x's and y are to the quadratics. So I can't tell you what your f is, that's fourth dimension. You know, I don't know what that is, but just those dimensions right there is an elliptic paraboloid. Now, what bums me, well, no. If you move the 4 over, then you'd have z is equal to, yeah, so, it just seems like to me it should be folding downward. The bowl should be turned over, but I don't guess it is. I'll take the word for it. They don't do anything but draw a picture. That finishes 13.6. Homework exercises here include either 3 or 5. They're both at Calc Chat. 3's at Calc View. Either 7 or 9. They're both at Calc Chat. 7's at Calc View. Either 11 or 13. They're both at Calc Chat. Any of the odds 15 to 19, they're all at Calc Chat. 17's at Calc View. Either 21 or 23, they're both at Calc Chat. 25 or 27, they're both at Calc Chat. 25's at Calc View. Any of the odds 29 to 37, they're all at Calc Chat. 31's at Calc View. Either 39 or 41, they're both at Calc Chat. 41's at Calc View. Either 43 or 45, they're both at Calc Chat. 47 is using the function and tells you several things to do with it. 49 is investigation about a point. So they say you need a computer, or you need some sort of graphing utility. So if you can do it without it, do it. If not, forget it. 51 is in exploring the concept, so you can think about doing that if you want. 53 is a topography question, so that's a pretty good one to look at. 57 is a temperature question, that similar to one we did in the book. Then they both are at Calc Chat. 57 is at both Calc Chat and Calc View. 59 is at both Calc Chat and Calc View. There's a couple true false, 61 and or 63. They should both be at Calc Chat. 65 is finding a function that works, so you can try that one. It should be at Calc Chat. 67 is using a function that you should be able to do, and it should be at Calc Chat. All right. That's it for 13.6. What we were just doing. I forgot. Sorry about that. Let me erase my stuff and show you how they do example 8. Okay? First, they take the gradient being the partial with respect to f, with respect to xi, partial with respect to yj, partial with respect to yzk, and plugging them in, 2xi plus 2yj minus 4k. At the point 2, -1, 1, then you plug that in, be 4i minus 2j minus 4k. Okay? Minus 4k is not going to change. Okay? Now, they show the maximum increase. That's supposed to be the gradient. 4i minus 2j minus 4k. For the life of me, I don't see a minus 2j. I don't see it going back to in this direction at all. It looks like it's coming just straight down here. And maybe I'm seeing something wrong with it, but it just doesn't seem like it has enough of a down, side of it. The minus 4k is okay. Doesn't seem quite far enough, but it's all right. It just seems like this should be pointing a little bit more back, because I don't see any y component on that gradient. And I think it probably should be back a bit like this. But I can't draw them, so I'm going to put that alone too. And there's a function, and that's it for 13.6. All right. Let's move to 13.7. We don't have much time left. Oh, about 18 minutes. So let's do what we can in 18 minutes. All right. Still in Chapter 13, functions of several variables. Now we move to tangent planes and normal lines. Okay? What we're going to do now is find the equation of tangent planes. Now, I don't know if you remember how we have an equation for a tangent plane. Because a plane is flat, all the variables are linear. So you don't have any quadratics, any cubits, any fractional powers, everything's to the first power, okay? Normal lines, okay, lines are everything first power. Find the angle of inclination of a plane in space. Of course, we've got to define what you're talking about there, and then how we find it, and we'll compare the gradients del f, which is gradient of f, xy, and del capital F, xyz. So we got to figure out what in the world they're talking about there. What's the difference in little and capital F's? Okay, so let's start with tangent planes and normal line to a surface. You have representative surfaces in space. Primarily, z is some function of x and y. So you have some surface up here as a function of x and y in the xy plane. That's the surface S. In the development to follow, however, it's convenient to use a more general representation. This is where it's coming from, that capital F is now a function of x, y, and z. And what you've done is do this thing minus z, that's equal to 0. That then becomes your function of x, y, the capital F function of x, y, and z. This is not the little f, capital F of integration that we used to do. So don't get those confused. This is just changing from z as a little f function of x and y to capital F as a function of x, y, and z is equal to 0. It's just little f minus z. Okay? So for a surface S given by z is equal to f of x, y, you can convert to the general form. Capital F as a function of x, y, and z is equal to little f of x, y minus z. Just what I said. Okay? So that's what capital F is here. Now, because little f of x, y minus z is equal to 0, you can consider S to be the level surface of capital F given by f of x, y, z is equal to 0. The level surface of F. Okay? That's also what S is. Now, if you remember, when we have functions of x, y, and z, what you have is not a level curve, but a level surface. So if you had x, y, and z, and you had a function of that equal to 0, then your surface would be the surface at various meanings, values there that makes that true. Okay? Whereas a level curve is a two-dimensional thing of a surface, a level surface is a three-dimensional representation where all of the values are equal. Okay. So here's example 1. They jumped right into example 1. For this function, capital F of x, y, z is equal to x squared plus y squared plus z squared is equal to minus 4. Okay. Now guess what? This is not one that you could write little f of x, y minus z is equal to this, is equal to 0. Okay? This isn't, because you can't isolate the z that way. So this is a different kind of problem, but it's some function of x, y, and z. Now describe the level surface given by this function equals 0. Now that's going to be a lot easier to describe. Okay? Because if this function is equal to 0, you can add 4 to both sides, and then what do you have? X squared plus y squared plus z squared is equal to 4. What does that describe? All three of these coefficients are the same, everything plus. What does that describe?
That's the equation of circle with a
Not an ellipse.
sphere.
A sphere, a perfect sphere, because it's an ellipse with all the axes equal. Okay? So that is a sphere. It's a special case of an ellipse. Okay? And their radius is equal to 2. Right? It's a sphere of radius 2. That's the level surface given by f of x, y, z is equal to 0. Okay? That's it. Let's see what they say. The level surface is that, can be written as that, which is the sphere of radius 2, whose center is at the origin. I didn't say that, but the center is at the origin, because there's no x minus something, or y minus something, or z minus something. Okay. So, got it. That's all the first example was. Okay? Now, moving on. Normal lines are equally important in analyzing surfaces and solids. For example, consider the collision of two billiard balls. Any of you play pool? Okay? Okay. When a stationary ball is struck at a point P on its surface, it moves along the line of impact determined by P and the center of the ball. So if you have a ball here, okay, and you hit it right here, then it's going in that direction. hit it straight to a pocket there, then hit it flat on. If you want it to head down this way, get at a point whose, when you combine with the center of that, it's going to send it that way. Isn't that how you play? You see what point you want to hit, and then you aim for that and hope you hit it. Okay. The impact can occur in two ways. When the cue ball is moving along the line of impact, that's if you're right in that, then yeah, you hit it square on, okay? The cue ball stops dead and imparts all of its momentum to the stationary ball. This is physics, okay? However, if you're having, if the pocket were over here and that's where you want it to go, yeah, you're fine. Set it up and go. But if the pocket's over here, you don't want to hit it there. That's going this direction. You want to hit it somewhere here so that it will go to the pocket in that direction. Okay? So if that's the case, the cue ball is not moving along the line of impact. The line of impact is here, cue ball's there. What you want to do, see, now the ball's going to go here. The cue ball, because it doesn't lose all its momentum, it's going to go back. Along the way they're drawing it here, along the goodness, I can't think of what they call it. It's the level surface or level curve. It moves along the level curve while the ball moves perpendicular. They always move perpendicular to each other. So if this is going in this direction, that has to go along the level curve. Okay? Now, it's deflected to one side or the other and retains part of its momentum. The part of the momentum that is transferred to the stationary ball occurs along the line of impact, which is the point of contact through the center. So that's the line of impact. Regardless of the direction of the cue ball, as shown here, this line of impact is called the normal line to the surface of the ball at point P. So there is the normal line to the ball. If that's where you hit it, then it's going perpendicular to that normal line. The cue ball, however, is going in the direction of the normal line, always perpendicular to the movement of the ball. The process of finding a normal line to a surface, you are also able to solve the problem of finding a tangent plane to the surface. The normal line is going to be along the tangent plane. So let S be a surface given by f of x, y, z is equal to 0, just like we did before. And let P, come on back, okay. I don't know why it does that. I wasn't doing a thing. Let me make sure my power's still on. It is. Okay. And P be some point x0, y0, z0 on that surface S. If C is the curve on S through P, that is defined by the vector value function, okay? C is a curve on the surface through that point P. So this would be that normal line, I think is what they're talking about here, defined by some R of t is equal to x of ti plus y of tj plus z of tk. Generic form, okay? Then for all t, f of this x of I, y, z has got to be 0, okay? Because it is the surface here and the vector value function is on that surface. So there's a surface, this function's on the surface, so this has got to be on the surface, okay? Now, what are our steps here? We don't have much time. If f is differentiable and the x prime of t, y prime of t, and z prime of t all exist, then it follows from the chain rule that 0 is going to be your F prime, capital F prime of t. In other words, your f sub x, the x, y, t, times x prime of t, that has to exist, plus f sub y, x, y, z, times y prime of t, plus f sub z, x, y, z, times z prime of t, that's got to be equal to 0. Now, just to give you an idea of what's going on here, in case, this is the easy way to write it, but this is what it's saying. Let me get my pen back. This is partial of f with respect to x times dx dt. So, and this is equal to partial, let's see, derivative of f with respect to t. And that's equal to 0, because that's what it says. This is df dt. And if that's 0, okay, and certainly if the function is differentiable and the function is equal to 0, its derivative is equal to 0, and then this would be plus partial of f with respect to y times dy dt. This is just how we did the expansion of our differentials. Remember, partial of f with respect to z times dz dt. Okay? Yeah, that's what this statement's saying. Sometimes it's not as easy to see when they use the subscript notation, but that's exactly what our expansion was of this. Okay? Now, at the point x0, y0, 0, the equivalent vector form is, this is your del, your gradient of f, at x0, y0, 0, and this is your r prime of t at x0, y0, 0, z, 0, x0, y0, z0, which is what your x is when t is equal to 0, y when t is equal to 0, and z when t is equal to 0. Well, this is your tangent vector, and there's your gradient, and the dot product of those is if you think back on it, your tangent vector is along that level curve, if this was two-space, and the gradient is perpendicular to that. So sure enough, the dot product's got to be 0. So this is saying kind of the same thing we had then, only this is for surfaces. This would be your gradient of the surface, dotted with the tangent plane to the surface, or tangent vector to the surface, and that's got to be 0. Okay? The result of this means that the gradient at P is orthogonal to the tangent vector for every curve on S through P. So that all the tangent lines on S lie in a plane that is normal to the gradient vector, okay, and contains the point P, okay? Now, that's what it's describing here. If this is the surface here, the gold-looking thing is the surface, and then every tangent line is perpendicular there, which is what we just said it was, then that defines this plane that is tangent to that surface, only touches at one point, and it falls away in every other direction. That's your tangent plane for that surface S. Okay. Now, is it time? Okay. What's that? Okay, let's see what the next slide is. This is this definition, so we'll pick up here next time. Now, if I'm not mistaken, I think I'm probably right on this. Nope, I have been here before. Okay, sorry. I was going to say this may be as far as I've made it in this book, in this course, but I have made it further because I have a mark there. Oh, yeah, I've gone further than this, so I couldn't remember there. So we'll pick up there. Let me give you a few homework examples in this. We only did one example. So homework, I would say do either 3 or 5. They're both at Calc Chat. 5's at Calc View. And stop there because we haven't done the tangent plane yet. We introduced it but haven't gotten there. That's the only thing you've got to do there. All right. Now, let's just look ahead a moment. We got to do 3-8. Finish 3-7, 3-8. And I think we probably skipped 3-9. I don't think I have time to do 3-9. 13-9. I keep saying 3-9. Lagrange multipliers, we'll probably just do a slideshow of that. I don't think we have time to do that. And then review exercises. So we just have a little bit more. No, we have applications of extrema. So yeah, we have 3-7, 3-8, and 3-9. So when we get back sometime that next week, it'll be your next test. I thought it might be this week, but I didn't know we weren't going to meet Wednesday. So it'll probably be next week. Moving along, then we're going to do chapter 14, and then the last chapter is 15. We may not get through with 15. I kind of doubt it. So far, I don't think I've ever made it all the way through 15, but we'll get as far as we can.
Do we have a final?
The final will be your last test. Whatever final last test, it'll be whatever chapter we're in. When it runs out of term, I'll give you the test of what we've covered that far. Okay. Good deal. Have a good 4th of July break. You get an extra day break. Sorry about that, but get over it. And we'll see you next Monday, a week from today.
We'll get our test one back.
What's that? I can give it back to you when I get them all in. I'll let you see your scores as soon as. I can't remember if I've graded this classes or not. Yeah, I started grading this one, but I didn't finish, so I don't have yours graded yet. But I'm going to try to get caught up with the 4th of July break. But we're going to be working a lot too, so I don't know if I'll make it or not. I'll give it my best shot.